warned me that this was a well-read group, but I had no idea how well. So I have designed this talk for what I would present to our first and second year nutrition students because I find that a lot of the information in here they don't have, even though they're well-read. So bear with me if you know it already, but I think I can usually pick up something. What I want to start out with is reminding you that combustion in a flame is the same chemistry as respiration in the human body. In each case, you're using some fuel, you're combining it with oxygen to produce CO2 and water. Same thing happens as we breathe. And there are the similarities. Using a fuel, combining it with oxygen, producing carbon dioxide and water, that releases chemical energy. The energy in the bonds, the carbon and largely the carbon-hydrogen bonds. And ultimately produces heat in the flame and in the body. The human body and the mammalian bodies, of course, use a different fuel. They largely run on free fatty acids, glucose, and a little bit your amino acids. They produce heat during those chemical reactions, but as we've talked about a little bit today, there's a coupling, metabolic coupling that goes on that uses some of that chemical energy, about 40%, to produce ATP. And it's that ATP that runs the rest of our body. We can measure energy metabolism a number of different ways. The way it's usually done now is to use indirect calorimetry, and what that means is that the measurement of heat production, which is calorimetry, is done indirectly, not by measuring the heat production per se, but by measuring either the inputs or the outputs or both to that chemical reaction. The burning of a fuel, combining it with oxygen, so you measure the oxygen consumption, and the output, the CO2 produced. And if you haven't seen them, the calorimeters are very simple devices. I mean, you simply have an enclosed system to capture the respired air from your animal, an inlet. This would be an open, what's called an open canopy indirect calorimeter, which you pull in outside air. You measure the oxygen CO2 concentration on the inlet. You pass it across the animal, measure the flow, the O2 CO2 concentration at the outlet. You measure the amount of oxygen that the animal consumes by difference and multiply that by the flow rate and calculate heat production. And although we won't get into it in this talk, if you also measure the CO2 production and the urinary nitrogen, you can also get at substrates, because the relationship between the three is unique. Protein's the only one that contains nitrogen. So if you measure urinary nitrogen, you can get at protein. And the relationships between oxygen and CO2 in carbohydrates and fats are dramatically different. So by measuring the ratio of CO2 produced to oxygen consumed, you can tell if you're burning carbohydrate or fat. Now, no matter what we do, as all of you know, there is a first law of thermodynamics, and it has to be preserved. We, as a human organism, cannot break that law. It's forgotten, however, by many scientists. And many papers that you'll read, you realize when you put the data together don't make sense because they can't balance the energy. So no matter what level of food intake you're at, there's got to be a balance between the calories that you consume whether or not you're laying down or using your body stores, your fat stores for energy, and the number of calories that you burn. That relationship cannot be broken. And as you all know, the fuels that we use, the free fatty acids, the glucose and amino acids, they come from our diet or our adipose tissue for fat, our glycogen for glucose, and a little bit for, okay, I like to move around, sorry, and a little bit from protein. Okay, and in balancing the calories in and calories out, I want to just remind you again of what the calorie densities of these different tissues are. Adipose tissue, which is about 80% fat, has a density of 7,800 calories per kilogram. Muscle tissue, which is mostly water, has a density of 1,200 calories per kilogram. And glycogen, which is a starch which is associated with water both intracellularly and extracellularly because of the excess water that it binds, has a density of about 1,100 calories per kilogram. So when you're looking at weight changes as a function of caloric restriction, it is important to understand what composition of that weight is changing. Okay. Starting point, reference point that you can think a little bit about. The textbook male, the 70 kilogram young adult, carries about 15 kilograms of adipose tissue, which is a little over 100,000 calories. About 2 kilograms of glycogen, which is all of 2,200 calories, not a day's worth, most of us. And skeletal muscle, about 28 kilograms. However, as has been mentioned here, you can't burn all of that and live, so I don't like to count it as an energy store. Death usually ensues with a loss of somewhere between 25 and 35% of skeletal muscle tissue. And the viscera, about 22 kilos. But the energy that's available for reserves during starvation or semi-starvation is about 120 kilograms in the adult male, non-obese male. In the female, it's about the same, actually, even though they're smaller, because the female carries about 10% more fat for their unit weight. Okay, other side of the coin, expenditure. I will talk about the three main components of energy expenditure. They're the resting metabolic rate, which I will have up here as RMR on most of my slides, the thermic effect of meals, TEM, and the energy expended in physical activity, EEPA. The largest component in humans is usually the resting metabolic rate. Exception would be an elite athlete who does a lot of training. Their energy expended in physical activity would be greater, but for most of us, it's the resting metabolic rate. Okay. What is the definition of resting metabolic rate? It's the rate of energy expenditure when a subject is lying down at rest, at thermal neutrality, which comes back to some of the things Jimmy was talking about, so that you're neither heating up, trying to stay warm in a cold environment, or trying to stay cool in a hot environment. And it's measured about a half day after your last meal. Some people forget that, right? Yes. As you're reading the literature, you may find this referred to as basal metabolic rate. That's the older term. Resting energy expenditure, which the Europeans tend to use a lot more. or sleeping metabolic rate, which is now easily measured in many studies. Sleeping metabolic rate tends to be a little bit less than a resting metabolic rate, which would be measured, say, when you're awake in the morning but haven't had breakfast yet, 5 to 10%. Well, actually, 1 to 5% less. So it is a little bit different. And it's actually this difference between resting metabolic rate and sleeping metabolic rate that has caused a lot of people to say, well, let's not call this basal metabolic rate because it's not the lowest. Basal meaning lowest.
There is a question about that, sir. When they measure sleeping metabolic rate, does that depend upon when meal time was taken or not? Is it independent of food consumption prior to
Try to repeat
Back.
the question.
Thank you. Question was, what's the definition of sleeping metabolic rate, basically, and how is it defined relative to the last meal? In most studies, sleeping metabolic rate is defined as the lowest period of oxygen consumption that occurs during the night for a period of something on the order of 1 to 3 hours. It tends to be the period in the late night. Most people in these studies will have eaten a dinner, somewhere around 8 p.m. So yeah, it's not as far out. It's not that 12 to 15 hours out after your last meal, but it is still lower than a morning resting metabolic rate in half the people. The components of resting metabolic rate, as we measure it in the human, basically you measure the oxygen consumed by the whole body. But want to remind you that every tissue does not consume the same amount of oxygen per unit weight. Adipose tissue is fairly energetically metabolic inert, only about 4 calories per kilogram of weight across a day. Skeletal muscle, 13 kcals per kilogram of weight per day. And the big three are liver, at about 200 kcals per kilo per day, brain 240 kcals per kilogram per day, and the kidney and heart about 440 kcals per kilogram per day. Which means that the sum of liver, brain, kidney, and heart, which add up to all of about 3.8 kilos out of a 70 kilo adult male, or 5.5% of their body weight, accounts for almost 60% of your resting metabolic rate. And that's important when you think back to Dr. Prola's picture of the organ size differences in the CR mouse versus the control mouse. One of the reasons they require less energy is they have smaller organs with high oxygen requirements. Okay, I said RMR is the major component of your 3 routes of energy expenditure. Most people, it's between 40 and 60%. Those in which it's 40 are usually athletes or people who are very active. For most people, it's more in the order of 55, 60%. And as you might guess, it's a function of body size. Bigger you are, the more likely you are to have a high metabolic rate. On a first approximation, it's about 0.9 kcals per kilogram body weight in females and 1 kcal per kilogram body weight in males. It also depends upon body composition. The more fat-free mass you have, or the less metabolically inactive fat you have, that influences your resting metabolic rate. The best equation for working through that is one from Cunningham, which is 21.6 kcals per kilogram of fat-free mass, everything except your fat, your triglyceride, not your adipose tissue, but your triglyceride, plus 370 kcals. and let me remind you, when I talk about fat-free mass, what I mean is everything except extractable fat. If we grind you up and extract out the triglyceride with ether or something like that, the remaining would be your fat-free mass. And when I talk about fat mass, I mean the triglyceride mass. So I am differentiating it from adipose tissue. Adipose tissue is about 80% fat, 20% actually cell and blood vessels and the like. And then the important one for this talk is that resting metabolic rate also depends upon your level of caloric intake. There is a range in humans of about plus or minus 200 calories, so that it decreases during low caloric intake and increases during high caloric intake. The fourth component, which I didn't have up there, is something that both Dr. Prola and Dr. Barger brought up, and that's this brown adipose tissue metabolism, or thermogenesis. In most tissues, in the mitochondria, there's a very strong coupling between oxidative metabolism, the burning of our glucose and fatty acids to CO2, and the production of ATP. In brown adipose tissue, there's a protein called uncoupling protein, which short circuits the coupling between oxidation and ATP formation. In normal coupled oxidative phosphorylation, you burn the fuel, you produce a proton gradient or an acidic gradient across the inner and outer mitochondrial wall, and when you leak that, or when you let that proton back into the inner mitochondrial space, that's coupled with ATP synthesis. With uncoupling protein, that proton, that acidic hydrogen, leaks back into the mitochondria without being coupled to the ATP synthesis, so that what you get is heat production from the burning of fuel, but no ATP or no usable energy by the rest of the body. And what that does is it allows an animal to stay warm on a cold day, and it also allows an animal to burn off excess fuel to keep weight down instead of gaining weight. Now, small animals, mice, rats, tend to have a very active brown adipose tissue, and because of that, you can get variations in resting metabolic rate, the amount of oxygen that they consume when not being physically active, that vary by a factor of 2. Put them in a cold environment, they can double their resting metabolic rate. Overfeed them, they can double their resting metabolic rate. Underfeed them, they can drop their resting metabolic rate. In humans, as I'll present some more data as we go along, although we are born with a fair amount of brown adipose tissue, that as a percentage of our body weight drops dramatically, so that by adulthood it's a very small number, fraction, percent or something, so that the ability to do this uncoupled thermogenesis is very small, and estimates are that it's somewhere between 3 and 9% that we can increase our resting metabolic rate by doing uncoupled thermogenesis. Well, the question is, 3 to 9% can add up, and yes, it can. 9% of calories per day, and most of us, 180 calories. That's not zero, and it can lead to a small weight gain or small weight loss. Okay. I indicated that the equation that I like for resting metabolic rate is 21.6 times kilograms of fat-free mass plus 370. That equation is the dark line here in the relationship between RMR on the y-coordinate and fat-free mass on the x-coordinate. And around that is an area of normality where people will lie. There's a lot of scatter around that equation. The prediction of resting metabolic rate from fat-free mass has an uncertainty of about 7 to 10%. Now, what that means, though, is if we're going to talk about changes in resting metabolic rate with caloric restriction, we have to find some statistical manipulation which will let us decide, is it dropping normally as predicted by fat-free mass, or is it dropping abnormally? And I've tried to show that with the 3 arrows up here. The 2 black arrows indicate a decrease in resting metabolic rate associated with a decrease in fat-free mass. They're staying in the same slope as the normal line. So that would be a decreased resting metabolic rate, but it wouldn't indicate any biochemical adaptation. The red arrow would be a change in which the resting metabolic rate changes faster than what you'd predict from the change in fat-free mass. And that would indicate that there's probably some metabolic adaptation, that there's some change in the oxygen consumption per unit of body mass. Okay, and then just to finish up the other terms, because they'll come up a little bit later on. The thermic effect of meals is simply defined as the bump above resting metabolic rate that occurs for a period of about 5 to 6 hours after you eat. If you're lying down, eat a meal, your resting metabolic rate will increase, and it'll increase by 30 or 40%, but only for a couple of 3 hours, and then by 6 hours you'll be back to that baseline again. And the area under that curve, under that bump above resting metabolic rate, is equal to about 10% of the calories that you consume. In some people it's as low as 3 or 4. In other people it gets up to about 12%, but the average is 8 to 10%. In the literature you'll find a lot of different names again: specific dynamic action, dietary induced thermogenesis, or the thermic effect of food. All pretty much mean the same thing.
Does that depend on the size of the meal?
Yeah. Well, actually there are a couple things. The more calories you eat, the larger the calories that show up in thermic effective meals, but the percent's about the same. You can actually, if you go the other way, if you eat a lot of little meals and eat them at the calories at about the same rate that you're expending, you won't see it. It'll actually go away. And most of it's associated with the storage of the energy from your meal. You have to convert that back to glycogen, back to protein, back to triglycerides, and those chemical reactions require some energy. But there may be a little bit of brown adipose thermogenesis mixed in here too. Okay, well, there's your question. So it depends upon meal size, but also composition. A high protein meal induces a much higher thermic effect of meals than the others. But you do have to push it. You can't just a little bit more protein, a little bit less fat, then you don't see much change. You really have to go to like 50% of the meal is protein. And then the energy expenditure of physical activity is just what you'd expect it to be. It's the energy expended above resting metabolic rate due to movement, due to physical movement. Yes?
A lot of the literature of weight loss, if you exercise, you're not
Okay, the question is, how much truth is there to the claim that resting metabolic rate increases after exercise? The answer is not a whole lot. An acute bout of exhaustive exercise, high intensity exercise, where you're working at running speeds, not just jogging, you will have an increase in the resting metabolic rate that's very measurable for about 30 minutes after the end. And then it'll still be a couple of 3 to 5% increase in resting metabolic rate for up to 24 hours. In exercises that are less intensive, leisurely walk, even a brisk walk, you won't have any measurable change in resting metabolic rate. And there's no correlation between resting metabolic rate adjusted for fat-free mass in active people versus inactive people, unless that activity is about, again, a very intensive exercise within the last 12 hours or so. And to tell you the truth, even if you go through the calculations of how many calories is that, the calories in that bump in RMR is less than 1/5 of the calories expended in the activity. So it's the activity that's the main determination. What about muscle building physical activity resistance training? If you bump up your fat-free mass by doing weight training and buff up, you will increase that, and as expected, you would see an increase in resting metabolic rate due to the increased fat-free mass.
Not to the activity itself.
Again, there are two things. One, there is an increase for 30, 60 minutes right after it. You'll have that going on. It's two things. One, it's the repayment of the oxygen debt during the activity. Most of those high-intensity activities, weight training very much so, you do a lot of anaerobic metabolism. You have to pay that back. You have to process the glucose that's gone to lactate. You've got to take that lactate back to glucose. That takes some energy. So you're repaying an oxygen debt. You see that. There's also an increase in resting metabolic rate if you damage muscle tissue and the like, and you have to repair that with a serious resistance bout. You will do that, so you'll get a bump there. But again, the amount that you burn in the exercise far exceeds this tail. Okay, we'll skip this one. But you can predict your energy, well, I'll have it here. You can predict your energy needs by adding up your calculated resting metabolic rate, adding in your physical activity and the like, but it's a pretty poor calculation. At best, it's plus or minus 15%. So most of you probably wouldn't be interested in the answer. Okay, now to the topic. Given that background, given those definitions, what about caloric restriction? The most famous human caloric restriction study is the Minnesota study. I don't know if any of you have read it. It's in a 2-volume text by Ansel Keys and Brozak. I can't remember his first name right now. Brozak was the first author. It's a marvelous, marvelous text. It was a study that was done in 1946, and it was actually not to study the caloric restriction. It was designed to study how you would refeed people who are starved. And in 1946, there were a lot of people in Europe who had been starved. So step one, before you could study that, though, was to create a starved population. And Brozak and Keys went out and recruited 32 conscientious objectors. From what I've been told by some of their students, they basically went out and said, you know, you've been accused of being cowards, you know, you're not going into the army. Come prove how brave you are. Join my study. Yes?
Did they get adequate nutrition?
Yes, we'll get to there. Their control diet was about 3,500 calories per day. They went on to a 6-month, 1,600 kcal per day diet on average. Some were higher, some were lower. And it was designed and adjusted on a weekly basis so that they'd lose about 25% of their body weight. And if you did the simple calculations, 3,500 calories a day minus 1,600 calories a day is a difference of almost 2,000 calories a day times half a year. That would be a deficit of 342,000 calories. Remember, I said the 70-kilo textbook male had about 120,000 calories of stored energy. So something must have happened to keep them alive. There must have been a reduction in their energy expenditure, or they would have, excuse the phrase, made an ash of themselves. Yes?
Well, I've always suspected that absorption of energy is connected to how well fed you are. A lot of the food goes right through you when you're fat. And
Yeah, not true. Paul Webb did some extensive study. Oh, the question was, does absorption of energy change as a function of plane of nutrition, how much you're eating or not? And the fact is, no, very little. You absorb about 95% of the calories that you eat, whether or not you're eating a huge amount or a little amount. Now, if you overload the gut on a single day, and I mean a huge overload, eating like 5 times your normal amount, yes, that can happen. You can get a malabsorption syndrome.
I'm not talking about
But normally, no. There's very little variation in that.
I'm